Can somebody start recording? Okay. All right. So we saw last time that if you have an m-dimensional basis of 1 electron spin orbitals, then for n electrons, we can form an exact wave function within this basis by linearly combining all determinants that can be formed. The number of determinants is MCN. We showed this by taking an example of a 2-electron function and then saying that this 2-electron function can be considered as a 1-electron function, keeping the other electron coordinates as a parameter. In which case, the combination coefficient is a function of the other electron, which again can be expanded as a linear combination of the same basis, giving you a set of products, combination of products. And of course, since that electron is products, become a determinant. So that is how we got the determinant. So it's a very simple thing. It's a linear combination. And those combination coefficients can be found by a variation procedure, which we will call linear variation. Because unlike in Hartree-Fock, here the coefficients which are linear expansion, those are the only coefficients that we have to find. Okay. So let me now look at a basis in which we will do the CI. So a convenient m-dimensional basis is a basis of the Hartree-Fock occupied orbitals plus all virtual orbitals. If you note that in the Hartree-Fock we solved a one particle equation. I just remind you the equation. In this equation, n spin orbitals which have the lowest energy, lowest orbital energies, were used to obtain the Hartree-Fock determinant, right? However, this one particle eigenvalue equation in principle gives a large number of orbitals. In fact, as large as you can determine. Of course, this largeness was eventually reduced by introducing a basis. I can remind you, introducing a basis. So the number of basis function then becomes the determining part of how many you can get. So first of all, if you remember, we did a spin adaptation for the RHF to special orbitals and then expanded the special orbitals in the basis of atomic orbitals. And if I have n k number of bases, then I got the Ruthan equation in a k by k system. I hope all of you remember this, the Ruthan equation. This is the diagonal matrix containing the spin orbitals. Okay. So I can get k number of spin orbitals in a k basis. And if it is a special basis, then my m becomes 2k. That's the number of spin orbitals. So that I construct later by adding alpha or beta spin. Out of these 2k spin orbitals, n of them are occupied. Right? So these are, let's say, occupied. And then the rest of them I call unoccupied orbitals. I hope all of you remember the Hartree-Fock. So there is a gap between the occupied and the unoccupied if the system is stable. Okay, and this is called the HOMO. This is called the LUMO. And they have interpretation in terms of ionization potential and electron affinity. I hope all of you remember this, right? So what I'm trying to say that together entire 2k number of spin orbitals that I get, which is much larger than the n, is a set of basis orbitals, which is very convenient because at least a subset of the n spin orbitals out of this 2k constitute a determinant which already gives me 97 to 98% of the total energy. So I have a Hartree-Fock determinant from here, which gives me a very large component. So I want to improve on that. So it is better to start from the same set of spin orbitals. So that is basically doing a CI in a Hartree-Fock basis. But I must say that when we are writing this theorem, I can take any m-dimensional basis. It is not necessary to take the Hartree-Fock basis, but it is convenient to write the CI problem as a Hartree-Fock basis because that's a basis in which one determinant already gives me 97 to 98% of the total energy. Is it clear? The reason we take the Hartree-Fock basis? Hello? So when I'm writing this, I have one determinant out of this MCN or 2KCN, which I call Hartree-Fock. Let's say C0. And then you have all other determinants. Together, the number of determinants would be MCN, but in a k-dimensional Ruthan equation, M is 2K. So your total number of determinants here would be 2KCN. Is it clear? Because finally you have to write it in terms of spin orbitals. If there's any question, please ask me. Is it okay? Can I proceed?
Hello.
Yeah.
Hello, sir.
Yeah.
Sir, totals. The size is the total.
Total exact wave function. This is the total wave function. Yes.
Yeah.
And the phi is a determinant, Hartree-Fock determinant.
Oh. So we can write in the all are single determinant form.
These are all single determinant. See, determinant essentially means a single determinant. So each of them is a single determinant. I have MCN such single determinant, right? Because for a single determinant, I require only n bases. So how many ways I can choose n out of m? MCN.
MCN.
So that's the number of determinants. Out of that, one of them is Hartree-Fock. Because I have taken Hartree-Fock basis. So in a HF basis, one of them is already Hartree-Fock and the rest I will now consider. So this is a determinant, of course. It's a Hartree-Fock determinant, RHF determinant. So we are, of course, looking at RHF and improving the RHF wave function. Okay. So now out of the MCN,
linear combination of other single determinants.
All determinants are single, but the overall wave function is not a single determinant because it's a combination, right?
Okay, sir.
Okay. So now we are considering. So let's say this is n electrons, some number. What will be another MCN determinant? How do I generate this? So these are my virtual orbitals. So take an example again for let's say 2 electron system. So I have two. This is my spin orbital, and then I have virtual orbital like this. Let's say I have only 4 virtual orbitals. So my 2K is 6. So I'm simplifying the problem. So I will of course have total number of determinants will be 6C2, right? So how will I generate the 6C2 determinants? They will be generated by, one is this determinant itself. Another determinant could be, set of determinants could be to lift one electron from here and distribute to any of these 4. You understand? Any of these 4. So there will be 4 such determinants. So one is Hartree-Fock. Then 4 determinants by lifting any one spin orbital here or a spin orbital from here. So total will be 4 plus 4, 8. It's 2 into 4. Is it clear? So I have 8. By taking one here, 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 or here, or taking this here, here, here. So 4 plus 4. I can, of course, take both the electrons here and distribute among these 4 spin orbitals. So how many ways I can distribute 2 in this 4? So this will be vacant. I take them here. So that number will be 4C2, right? That's 6. So this will be 6. And you can add this up. This is your 15. And 15 is 6C2. Is it clear? Just an example I have given.
Hello, sir. Can you tell me again, sir?
Yeah. So I have, see, total number of spin orbitals for this particular problem will be 6C2. You agree, right? Because your number of spin orbitals is 2 plus 4, 6. Number of electrons is 2. So you have a 6C2, which is 15. I'm now categorizing this 15. Out of 15, one of them is a Hartree-Fock. Then another set can be obtained by lifting any one electron from here or here to any of the 4. So how many I will get? 4 plus 4, 8. One of them will
Yes.
remain here, one of them will go here. Then both can be lifted. So I will have 4C2, that is 6. You add this up, you get 15.
Okay, okay, sir. Understood.
Right? Yeah. So this kind of determinants where I have lifted only one electron from one occupied, this is occupied, one occupied to one virtual spin orbital would be called singly excited determinant. Remember, we are looking at a ground state wave function. So don't get confused with this excited. This is only a singly excited determinant with respect to Hartree form. Because I'm mixing those determinants, I'm only categorizing. This 6 would then be called doubly excited determinants. I end here because my problem is only 2 electrons. So I can't have triply excited because there is no more electrons to excite. So if you look at it in this manner, just like I did for this simple problem, all 2kCn determinants in a Hartree-Fock basis can be categorized in the following manner. Hartree-Fock, then all singly excited, all doubly excited, and so on. Triply excited, quadruply excited, till I reach n-tuply excited. Correct? These are all determinant. They are not excited states. I am again repeating. So I can have one electron excited from one occupied to one virtual, 2 electrons, 3 electrons, n electrons. If I sum all of these number, this number has to be 2kCn. So if you want to know a little bit in more detail, since I have n spin orbitals, I have basically n occupied orbitals, correct? In terms of the Hartree-Fock notation. Then how many virtual orbitals will be there? 2k minus n. Is it clear? Virtual orbitals are same as unoccupied orbitals. Like a LUMO. LUMO is one of them. Lowest unoccupied orbital is one of them. So I have total n occupied, n virtual orbital. Hartree-Fock is just one determinant where all n electrons are here. So what is the number? That number is only 1. Plus, how many singly excited will be there? Just like here I calculated. 4 plus 4, right? Here how many will be there? From each occupied orbital to each virtual orbital. So the number will be 2k minus n into n. Is it clear? Again, coming back to the example, your 2k was 6, n was 2, 2k minus n was 4, virtual orbital. So number of singly excited was 2 into 4, 8. So I'm doing exactly the same thing. 2k minus n into n. Is it clear? Number of singly excited. So this is singly excited. This is Hartree-Fock, of course, HF. The number of doubly excited was 2k minus n C2 times nC2. So number of ways that I can, here of course nC2 was 1. Number of ways that I can take out 2 electrons from the n spin orbitals and distribute in the 2k minus n. So that is your doubly excited. Then similarly you have 2k minus n C3 times nC3 and so on. Till at the end, you will have 2k minus n Cn into nCn, which is just 1. So here it's like this. When I take doubly excited, that was nCn. There's only one way taking out from here. So this will become my total number of determinants. So this is triply excited. This is your n-tuply excited. If you sum all of them, they must be equal to 2kCn. In fact, if you remember, these are the kind of combination problems that is to be given in school. So this is also the same way I can write 2k minus n C1, nC1. This is 2k minus n C0 NC0. That is 1 into 1. Right? So if you remember the combination, so this is just a combination problem. If you sum all these, I can show that this is actually 2k Cn. Just like here I showed, 2k was 6, 6c2, 15. Is it clear? Please ask question if it is not clear. So basically all the 2kCn determinants I have categorized as a Hartree fog and how they differ from Hartree fog. So they differ by single orbital, 2 orbitals, 3 orbitals, and n orbitals. When I mean orbital, I mean spin orbitals. Okay, if you have any question, please ask me at this stage. Is it okay? Can I proceed?
Yes, sir.
Yeah. Okay. Let me also give a symbol. So for Hartree fog, let's say I'm using phi Hartree fog. I think in Szabo and Oslund they have used psi, and the exact wave function they have written as phi. I'm not very sure, but doesn't matter. I mean, we will continue to use. So I write Hartree fog as a phi Hartree fog, and then I use singly excited determinant in the following manner. As a set of determinants where I take out one electron from an occupied spin orbital A to a virtual spin orbital, let's say P. So the notation that we are using is A, B, C, etc. occupied spin orbital, P, Q, R, S, etc. virtual spin orbitals. Okay, that's the notation I'm using. So all possible A, all possible P. So that is your 2k minus n into n. The one important thing to realize that what I have done here is to write the same determinant saying that only change is A to P. The rest are all identical. So that is the reason I'm writing phi AP. So whatever is phi Hartree fog, from where I would be able to generate this determinant very easily. So if you remember, phi Hartree fog has lots of columns, right, of spin orbital. The 8th column or 8th row will be replaced by the pth one. So that is the singly excited. It will differ from Hartree fog by one change of spin orbitals. Then you have a doubly excited where 2 out of n will be taken out. So let me call this phi AB and PQ. So 2 from A and B, they're dummy, they're all, of course, they'll be dummy index eventually because they have to sum up, and they get distributed to some PQ. And so on. So now we can see how to write it, A, B, C, P, Q, R, and so on, up to n-tuply excited determinant. So finally, I can write my exact wave function as C0 phi Hartree fog. Now I take a linear combination of all these. Sum over. This is not one determinant. All A, all P. So I have to sum over all A, all P. And I have a coefficient which I write exactly like this, CAP, phi AP. This is, of course, an n electron determinant. These are all determinants. Then I have got a phi AB, PQ, but all AB, all PQ in this manner, that A less than B, P less than Q. So basically, I am taking pairs of AB, pairs of 2 electrons. So again, A less than B, P less than. I hope this is clear, because A equal to B cannot be true. Because obviously, these 2 spin orbitals could never have been the same in the Hartree fog itself. So there is no way that you can lift electrons from the 2 spin orbitals. There is no way that you can put them in the same spin orbitals, unoccupied. So they are all going to be different. And of course, A equal to B, P equal to Q will be thus 0. And A less than B, P less than Q, or A greater than P, P greater than Q are identical. Okay. Multiplied by C, A, B, P, Q. And then you write A, B, C. So A less than B less than C, P less than Q less than R, phi A, B, C, P, Q, R, multiplying by corresponding coefficient, and so on. You can keep writing. That's not important. Let me analyze up to this point. I told you these determinants have a very special property that if I have phi AB PQ, this is 0 if A equal to B or P equal to Q or both, of course. Phi BAPQ is actually negative of phi ABPQ. Can you see this? Because here B is replaced by Q, B is replaced by P, A is replaced by Q. Here A is replaced by P, B is replaced by Q. So basically, if you look at these two determinants, A and B are not there, but P and Q have exchanged their positions, which means using the antisymmetry, it is negative of each other. Is it clear? Similarly, ABQP is negative of ABPQ. They have gone from the same place, but one has gone to Q, one has gone to P, so it effectively looks that P and Q are interchanged. Of course, if you interchange both, so phi BA QP, this will be identical to phi ABPQ. Because it just has the same B to Q, A to B, A to P. So in the same place, P and Q come. You can easily see this from a 2-electron problem. Well, let's say number of occupied spin orbitals is 2. Number of virtual spin orbitals also you can take 2, just to simplify the problem. So let's take a problem where you have 1 and 2, and you have 3 and 4 are virtual orbitals. So these are occupied. This is virtual. So I now generate, so this is my phi Hartree Fock. So let me just write down the phi Hartree Fock. Sorry. As a determinant of 1, 2. Now I'm generating 1, 2 to 3, 4. So I'm generating a determinant which is 1, 2, 3, 4. How will it look like? 1 will be replaced by 3, 2 will be replaced by 4, so it's 3, 4. I'm now generating phi BAPQ. So BA means it is 2, 1, 3, 4. So only here it is changed. So what happens? 2 goes to 3, 1 goes to 4. So it will become 4, 1 goes to 4, 2 goes to 3. And you can see now that this BAPQ is negative of ABPQ because 4, 3 is negative of 3, 4. And with that, you can actually check the rest of the things also. And if I interchange both, they'll come back. So if I write phi 2, 1, 4, 3, I interchange both, then of course 2 is replaced by 4, 1 is replaced by 3, so I get back 3, 4. So these two are identical. Is it clear? So what I'm trying to say, you need to only write A less than B, P less than Q. The rest of them are identical. Identical means they're linearly dependent. So either same or negative, which means you don't take a combination because we are only going to take linear combination of independent Slater determinant. Okay. If there is any question, please ask me before we proceed further. If that is so, then I just wanted to write to you that if psi 0, C0, phi Hartree Fock, now using the Dirac notation to write this, plus, so the whole thing is sum over AP CAP phi AP plus A less than B and so on. So I have these n-triply excited determinants, all of them. I'm just writing up to doubly excited, or you can write full. If you write full, then within this basis, it is exact. What is this basis? This is 2k basis. So this is n, these are 2k minus n, and so on. Occupied is n, unoccupied is 2k minus n. But in CI, I always told you that even to do up to 2k Cn becomes very big. All MCN determinants become very difficult to do because they are factorial problems. So full CI is often very difficult to do. So very often we do what is called truncated CI or incomplete CI. So one of the truncations that will be very, very popular is a truncation where I truncate right here. Why do I truncate right here? I will explain a little bit later. But I will say that within the correlation problem, the most dominant part is what is caused by excitation of two electrons from the occupied orbitals to the virtual orbitals. So excitation of two electrons from occupied to the virtual orbitals. And not, so here, for example, any two electrons to the virtual orbital. So that is actually most dominant part of the electron correlation. So that is why it's a very meaningful idea to do this. We'll come back to this part a little later. And this will be also realized when you are taught perturbation theory. But the point is that if I do truncation of CI, then up to here is a good truncation, and that will be called CI singles and doubles. That is how these names come. So you have CISD, then if you take triples, CISDT. If you take quadruples, you take CISDTQ also. Depending on what you take, you have approximations. So CISD is a good approximation. Within the singles and the doubles, usually again, as I told you, it is understood that this is more important. Because the electron correlation, I will later tell you that it occurs in pairs. So this is much more important. So very often, old days, people simply did CI doubles, not even singles. So you just remove this part. So you can make several different truncations, and they will become the context of incomplete CI or truncated CI. Is it clear? If there are any questions, please ask. Can I proceed? Yeah. Okay. Yeah.
So, as we have seen in the doubly excited states,
It is not
the
doubly excited states. It's a doubly excited determinant.
uh,
State is a ground state.
okay, yes, doubly excited determinants. The relation between exchanging the AB or PQ that you showed earlier,
Yeah,
that
yeah.
is something. So, can
Negative.
we extend this for any number of like triple excited
Yeah,
or
yeah,
any?
yeah, 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 yeah. Of course. So any pair, if you interchange, it will become negative
Okay,
because it is basically tantamount to interchanging the two columns or two rows.
okay. So it
And
is the same as the determinant
yeah, so
properties.
it's a determinant properties. And if you have two such changes, then again it will become plus. So it depends on how many changes you are making, right?
Okay,
Yeah,
okay.
sure. Okay. Can I proceed? Yeah. So now what is the most important question? The question that we'll ask, how do I calculate the coefficients? Whatever is my full CI, truncated CI, the parameters that I have to calculate or the variation by variation are the coefficients. Combination coefficients, and this is done by the variation method, and in this particular case this variation method will be called linear variation because your coefficients are just linear. The variation is occurring in the linear coefficients. So there is no c square, for example. If there is a c square, c cube, that would have become nonlinear variation. So I have only linear variation and I have to solve this problem. Now standard variation method is the following, if you remember, that I take psi h psi, here psi 0 is psi 0, subject to the fact that they are normalized unity. So subject to psi 0, 0 equal to 1, let's say, and then vary these with respect to coefficients, right? And then you will get the linear variation problem. You will get the coefficients. So I can do this for any number of any linear variation. It is not necessarily that I have to take n electron. It can be 1 electron also. So basically this problem is a very general problem where I can write the trial wave function in a basis. My basis here are the basis of spin orbital, a basis of determinants. For the n electron problem, my basis is the basis of this later determinant. These are my new bases. Originally, I started from 1 electron spin orbitals, but the MCN determinants form a complete set of determinant bases for the exact wave function. So I'm writing the trial function in this basis of MCN determinants. But the problem is very general. Any trial function in a basis, I should be able to do linear variation. So let me just quickly show you how to do it. So let me write a psi as a sum over Ci, some basis, I'll just call it chi I. So this is my basis. I equal to 1 to k. It can be 1 particle basis, 2 particle determinant, 3 particle determinant, depending on the problem, but doesn't matter. I want to find out this coefficient. So this is trial function. I want to calculate C tilde by variation method. I first assume that the psi tilde is 1. That's the first assumption. Then it would mean a condition on these coefficients. Let me also assume that the basis is an orthonormal basis. And note that in our case, these determinants also are orthonormal basis because we are starting from a Hartree-Fock orbitals which are orthonormal. So if you start from a 1 electron orthonormal basis, all these Hartree-Fock is orthonormal, then determinants formed will be also orthonormal, which means they are normalized unity and any two determinants overlap will become 0. So let us assume that this basis is orthonormal. Okay. Then what does this mean? The function is normalized. So it means if I do psi tilde, I expand both psi tilde and psi tilde in the dummy variable. So I, let's say the first one is I, second one is J, then I will have Ci tilde star, Cj tilde, chi I, chi j. I hope you can see this very easily. You must have done this. I have expanded psi tilde, Ci tilde star, chi I, psi tilde on the right as Cj tilde, chi j. And I integrate over chi I, chi j. That's the function. Ci star, Ci tilde, Cj tilde are numbers, they come out. If you very quickly see this, I can simplify because they are orthonormal basis. So it is a Kronecker delta. I must be equal to J. So it is Ci tilde star, Ci tilde equal to 1. This is 1. So this condition that the trial function is always normalized unity essentially means that the coefficient, if you take the modular square of the coefficient, all the k-dimensional bases, their sum is equal to 1. So it means sum over I equal to 1 to k mod ci tilde square equal to 1. Is it clear? So in an orthonormal basis, if this is equal to 1, it means that this square of all these, if I sum, they'd be equal to 1. Using this, now I can do a variation method. So what would be my variation method? It is psi tilde h psi tilde. Vary with respect to c tilde, subject to the condition that psi tilde minus 1 equal to 0. Or I can say subject to the condition sum over ci tilde square minus 1 equal to 0. So because this is identical. If you have any question, please ask. So what I'm doing is to vary these subject to a condition. I think in Hartree-Fock you have done very similar things, right? So what do? You use a Lagrange variation. You construct a Lagrange of psi tilde h psi tilde minus sum over I, and that is very important. For there is a mod ci square minus 1. That is equal to 0. There's only one condition. So you have to multiply that by lambda and basically make this stationary. So make lambda stationary with respect to c tildes, all the c tildes. So let me try to do this problem. But before I do that, I have to also expand this in terms of c tilde. So exactly the same way that I expanded psi tilde, I will exactly do the same thing. So let me rewrite the left-hand side. So what is my psi tilde, h psi tilde? Expand the left-hand side by dummy variable I, again in a k basis. So remember, my variation problem is psi tilde is sum over this k basis. This basis is very abstract at this point. I'm not exactly going to the determinant yet. But this is a general problem that I'm doing. Sum over I equal to 1 to k, ci star, ci tilde star, phi I, right? I have just taken, chi I. I have taken this as my basis function, chi I. So left chi I. Then you have h. Then expand psi tilde with another j. It will become cj tilde phi chi j. Where this chi I, chi j is the basis. So then my Lagrangian becomes sum over I, sum over j in the k basis, ci tilde star, cj tilde, phi I, h, chi I, h, chi j, minus the Lagrangian, which is nothing but lambda modulus ci square minus 1. So that is my Lagrangian. Now what do I want to do? This is everything in terms of coefficient. I want to vary this Lagrangian with respect to ci, one of the ci. So let's say ci tilde star. Note that if I vary with respect to cj tilde or ci tilde star, they are identical because this is a complex conjugate of each other. The equation will be identical. So let me do this exercise. So if I do a calculus of variation, again the same thing has been done in Hartree-Fock. If I do over a particular I tilde, what will happen? This dummy variable will not survive. So this will then become sum over j only. And this will also vanish. You will have cj tilde, chi I, h, chi j. Same thing will happen here. Minus lambda. If I do Ci tilde square modulus is Ci tilde Ci. If I take this out Ci tilde star, you will have lambda times Ci tilde. And lambda into 1, of course, you cannot vary, so that will be 0. So that will be your equation. Is it clear? I think you have done very similar things in Hartree-Fock. So I'm just quickly doing it. So I am taking out a particular Ci tilde star. This can be Ck tilde star, it doesn't matter. So you get Cj tilde chi I h chi j equal to lambda times only Ci tilde. Since I is a dummy variable, some people don't like to call it I. You can call it anything else. The same thing will happen here. I will be replaced by that. But it does not matter. If you construct this H matrix element between chi I, H, chi j, and let me call it a matrix. So let me call this a matrix, ijth matrix of the H. So it's a matrix now. This was an operator. This is a matrix. This H is a matrix. So if I take matrix element of this operator between chi I and chi j, I call H ij matrix, ith row, jth column. Then you can quickly see that this equation, variation equation, has now become sum over j equal to 1 to k, hij, then cj tilde equal to, now that there is equal to 0, I am putting this equal to lambda ci. You can quickly recognize that this is nothing but the matrix eigenvalue equation. And that will give you very easily the Ci problem. One can very easily show, after they get the Ci, that this lambda is nothing but the energy. So this is basically my energy. So the point that is done is the following, that I am doing a linear variation of psi tilde in terms of basis. So what do I first do? What is my step? First, what you do is construct this matrix element. Just construct this. Basis is known, Hamiltonian is known, construct the integrals, you get the matrix, and then the recipe is very simple. Simply diagonalize the matrix. So the recipe of a linear variation is diagonalize the Hamiltonian matrix in the basis. That's it. If you diagonalize, what is the dimension of this Hij? As much as chi I and chi j. So this is k by k matrix. Your k was the number of basis function, and then of course the energy will be also k, and everything is done. And now you know how to get it. For each energy, I have a column vector, which is the eigenvector, so I will get all the coefficients. But important thing is, in this linear variation, I am not only getting the one lambda, but I'm getting all the lambdas because I have an eigenvalue equation. I'm getting k number of lambdas. So I get not only ground state, but also excited states. And this is a very, very important part in a linear variation. And since I have used the normal variation method, I made this stationary. Of course, it has also an upper bound property. So you know all of these lambdas are greater than or equal to ground state, but there is something more that I will see later. But the upper bound with respect to ground state is of course there, but it has much more features that we will see. So the recipe is very simple. Construct the Hamiltonian matrix in the basis by evaluating these elements and simply diagonalize. So you can see that CI is a very, very simple procedure. It is just a procedure to diagonalize a matrix. Which matrix? The Hamiltonian matrix in the basis. And you get everything. If I come back to my CI problem with reference to Hartree-Fock orbitals, so this was my basis, Hartree-Fock, singly excited, doubly excited, and so on, which I wrote here, right here. So what is my job? My job is to construct, let's say I'm doing CISD. My job would be to construct the Hamiltonian matrix element using all these bases, whatever is the number, phi Hartree-Fock, phi AP, phi ABPQ. So if whatever is number, let's say its number is 50, then it will be 50 by 50 matrix. Number is 100, 100 by 100 matrix. Of course, numbers are very large, even for CISD. And then diagonalize. So if I have Hartree-Fock plus singly excited plus doubly excited number is 50, then I will also get 50 roots, 50 eigenvalues. And we will later see that they can be actually identified as excited state energies, actual true excited state energies. So in some sense, CI is very simple. It just means I have to find out in actual practice, how do you calculate matrix element between all these bases? Of course, one of them is walkover. That is, you already know this. Then you can have one phi A AP, H phi Hartree-Fock. You can have both sides singles, phi A AP, H, phi BQ, and so on. Then doubles with Hartree-Fock, doubles with doubles. So all kinds of matrix elements I have to construct. They become my matrix together. If I arrange them in the row and column, they become my matrix and then they diagonalize. So it's a very simple procedure. We need to know how to evaluate this. Have you done Brillouin's theorem? Hello?
No, sir.
No. Okay. So in the Brillouin's theorem, you will see there is a nice simplification. If I start from Hartree-Fock orbitals, so this is Hartree-Fock orbital, this is a virtual orbital, this is occupied, this is virtual. I will show that these matrix elements are all zero. That is Hartree-Fock with singly excited determinant. Hamiltonian matrix element is always zero. It's a very beautiful theorem. This will actually come as a Brillouin's theorem. I will do that later. And of course, singles and singles. Then you can have, of course, Hartree-Fock with doubles, like phi ABPQ, and so on. Doubles with single, all possibilities within the CISD. So you have to construct all these matrix elements. So if you know
Sir,
how, yes,
I have one question.
yes.
Sir, if I from one orbital take one orbital to another orbital, one electron case.
Yeah,
So there is a for singly excited
Determinant, determinant.
determinant.
Yeah.
So it is like seems like a perturbation in the system.
No, don't interpret it as a perturbation. I'm now construction of a determinant. So that's what I told you. Let's say I have a 2 electron determinant 1, 2. I replace 1, 2 by 3, 2. This is singly excited determinant. Because the electrons were in orbitals 1 and 2. Now one of the electrons which was in orbital 1 has gone to orbital 3. So my determinant is orbital 3, 2. 1 is now vacant. Now, perturbation is something different. You are trying to say how it happened due to perturbation. Yes, I mean, of course, that is not what I'm discussing. That is, if I am only giving this determinant, how do you go from here to here? That's what you are discussing. right?
So in the theory, sir, there is a if the second order energy correction, there is a in the denominator.
Yeah,
So
yeah, yeah.
there is a
That is
term is
right,
AM
right.
AM0. If it is 0, so
Yeah.
the second order correction is not valid. So you have to take the determinant form to what is it? Forget. The determinant should be non-zero value, sir. In case.
Anyway, so that is the brilliance theorem I'm talking of. That's exactly what I'm talking. I think that's what you're talking. We'll come to the perturbation theory.
Okay.
You're probably talking of this. So we'll consider perturbation theory later. I think you're already discussing perturbation theory. We'll do that formally and we'll connect it. No problem. So right now, please understand that all these determinants of the Hamiltonian, between the determinants, all the Hamiltonian matrix elements between the determinants can be formed by Slater-Condon rule. You already know how to write this determinant, right? By Slater rule, correct?
Yes, sir. Yes, sir.
So similarly, I should be able to write all this in terms of spin orbitals, 1 and 2 electron integrals. The
I
same one
understand,
and
but we have to connect this all the things. That's the
to connect to what? Perturbation theory.
the main process from Hartree-Fock to the CI and the other.
Yeah, that will do, perturbation theory. But Hartree-Fock to CI connection is very simple. In the Hartree-Fock theory, your wave function had only one determinant. In CI, your wave function is a linear combination of determinants. Hence, this is better.
Yes, sir.
That is their main thing. Right now, don't do any other connection.
Oh, okay, sir.
How to generate 1, 2, 2, 3, 2 is that not the question here. But I
Yes.
know that if I have this determinant, I also have such a determinant. It is possible to construct. So we are not doing any perturbation to generate this. It is possible to construct 3, 2 also by lifting an electron. What I am telling you is that the ground state wave function, again I'm repeating, the ground state's wave function also is a linear combination of determinants. But what I showed you is that during the process of CI, you not only get ground state, but you also get excited state energies. But all the wave function, even the excited state wave function, will also be a linear combination of the same determinants. The coefficients will be different. Combination coefficients will be different. So everything is now linear combination. You understand? So all wave functions will be a linear combination because we have shown that by 2 electron function, that in a basis, if you take all determinants, it's always an exact wave function. Be it ground state, be it excited state. So everything, including ground state, has excited determinants.
Okay.
So I am not doing here perturbation. Perturbation will be actually from the ground state wave function to an excited state wave function. This is completely different. If you assume that your ground state wave function is one determinant, this is also another determinant, then it is right.
So,
but none of them is one determinant. None of them is one determinant. Both of them are linear combination.
So from this, we just find out the upper bound of the energy. So that's it.
Yes. So we can find out by variation method the energies which will all be upper bound to the ground state.
So that's why I just improve just from Hartree-Fock to say from
Yes.
CI.
So I will come to that later how we have improved. So this was, let's say, my actual exact energy ground state. Hartree-Fock is here. If I do CISD, the result will come down, but they will still be greater than E0.
Okay, sir. Thank you, sir.
So upper bound will still be there, but also importantly, I am getting many other excited state energies. So you will like to know where will they be? They will of course all be greater than E0, but is there any other theorem? And that is where CI is very, very interesting.
Okay, sir.
Okay, that there will be theorem, there are exact excited states also, right? So there will be theorems of connecting various lambdas to those excited state energies. So the bound is much more general. Right now, whatever you have learned, that is anyway true, that these are upper bound to the ground state. All of them, all of them. But what I wanted to tell, when you do spectroscopy, you look at ground state wave function to an excited state wave function, not from a determinant to determinant. But chemists always think that everything is a determinant. So that is why you have this confusion.
Okay, sir.
You are thinking ground state is 1, 2, excited state is 3, 2. No, that's not true. That's in the Hartley-Fock picture. And it is very, very difficult for many chemists to come out of the Hartley-Fock picture. Because you are already fed with the 1 electron in 1 spin orbital. But that's not true. So what I am saying is that even the ground state wave function has a combination of these two determinants. Combination of Hartley-Fock, singly excited, doubly excited, and so on. When I do spectroscopy, I don't change determinants. I change the wave function, full wave function. Each of them is a combination of determinants. You understand?
Oh,
So saying that these determinants are by perturbation is incomplete. I would say it's not absolutely wrong, but it is an incomplete statement. Any other question is there? It's already late. I will stop today.
thank you, sir.
Yeah. All right. So our next class will be on Monday. So Monday I'll take both the classes because we want to move the CI forward now so that we can take both the classes on Monday. And after that, maybe I will still require one more class. So I will see how to close the CI before we can start on perturbation theory. Okay. Thank you very much. Okay. I'll leave now.